Αγαπητές φίλες και αγαπητοί φίλοι, Τρίτη 25 Φεβρουαρίου του 2025 σήμερα και σας καλωσορίζουμε και πάλι στα φυσικά. Σε μία εκπομπή η οποία ουσιαστικά είναι συνέχεια αυτής που δεν μπορέσαμε να ολοκληρώσουμε την Παρασκευή λόγω τεχνικών προβλημάτων. Για τους νέους κυβερνοθεατές μας αναφέρουμε πως τα φυσικά είναι μια 15ημερη εκπομπή η οποία ασχολείται με θέματα επιστήμης και τεχνολογίας που παρουσιάζουν ενδιαφέρον για τον καθένα και λαμβάνεται ιδιαίτερη φροντίδα να είναι κατανοητά από όλους. Μεταδίδονται στο πλαίσιο του διαδικτυακού καναλιού Ανιχνεύσεις Web TV του δημοσιογράφου Παντελή Σαββίδη, τον οποίο ευχαριστούμε για τη φιλοξενία. Για πρώτη φορά καταφέραμε να τραβήξουμε μια μεγεθυμένη εικόνα ενός ετοιμοθάνατου αστέρα σε έναν γαλαξία εκτός του δικού μας Γαλαξία. Ο αστέρας WOH G64 σε απόσταση 160.000 ετών φωτός από εμάς απεικονίστηκε χάρη στην εντυπωσιακή ευκρίνεια που προσφέρει το πολύ μεγάλο τηλεσκόπιο του Ευρωπαϊκού Νοτίου Παρατηρητηρίου. Ανακαλύψαμε ένα οειδές κουκούλι που περιβάλλει στενά τον αστέρα. Μπορεί να σχετίζεται με τη δραστική εκτόξευση υλικού από τον ετοιμοθάνατο αστέρα πριν από μια έκρηξη υπερκενοφανούς. Τα παραπάνω είναι δηλώσεις του δόκτορα Keiichi Ονάκα, αστροφυσικού στο Πανεπιστήμιο Αντρές Μπέγιο στη Χιλή, κύριου συγγραφέα μελέτης, η οποία δημοσιεύθηκε στις 21 Νοεμβρίου του 2024 στο επιστημονικό περιοδικό Astronomy Astrophysics, σύμφωνα με δελτίο τύπου του Ευρωπαϊκού Νοτίου Αστεροσκοπείου, ESO. Αγαπητές φίλες και αγαπητοί φίλοι, ο απόψινός καλεσμένος θα μας μιλήσει από το Σαντιάγκο της Χιλής. Μισό λεπτό όμως, γιατί έχουμε ένα πρόβλημα στη σύνδεση. Μισό λεπτό παρακαλώ. Αγαπητές φίλες και αγαπητοί φίλοι, ο απόψινός καλεσμένος θα μας μιλήσει από το Σαντιάγκο της Χιλής. Καλωσορίζω λοιπόν τον καθηγητή Κeiichi Ohnaka, επικεφαλής της ομάδας που πέτυχε να αποτυπώσει για πρώτη φορά σε μεγέθυνση άστρο που βρίσκεται έξω από το δικό μας Γαλαξία. Keiichi-san, welcome to φυσικά.
Καλησπέρα.
Καλησπέρα. Ο Keiichi,
να πούμε μερικά πράγματα.
Το παρακαλώ. Ο Keiichi Ohnaka ξεκίνησε τις σπουδές του στην αστρονομία στο Πανεπιστήμιο του Τόκιο στην Ιαπωνία, πρώτα στο προπτυχιακό πρόγραμμα, στη συνέχεια στα μεταπτυχιακά και διδακτορικά προγράμματα. Αφού πήρε διδακτορικό στην αστρονομία το 1997, εργάστηκε ως μεταδιδακτορικός υπότροφος στο Τεχνικό Πανεπιστήμιο του Βερολίνου στη Γερμανία και στο Πανεπιστήμιο του Τόκιο από το 1997 έως το 2000. Από προπτυχιακός φοιτητής εργάστηκε πάνω σε αστέρια που πεθαίνουν. Ειδικά κατά τη διάρκεια της περίοδου του στη Βόνη, άρχισε να εργάζεται σε κοντινές παρατηρήσεις αστεριών που πεθαίνουν στο υπέρυθρο φως. Στη Χιλή άρχισε να ασχολείται παράλληλα στη ραδιοαστρονομία, χρησιμοποιώντας το άλμα προκειμένου να τραβήξει ευκρινείς εικόνες αστεριών που πεθαίνουν. Μετά από αυτό προσλήφθηκε στο Ινστιτούτο Ραδιοαστρονομίας Max Planck στη Βόνη, όπου δούλευε και ο Μανώλης Αγγελάκης, τον οποίο θα δούμε στη συνέχεια, αλλά σε διαφορετική ομάδα. Εργάστηκε εκεί για λίγο περισσότερο από 14 χρόνια, αρχικά ως μεταδιδακτορικός υπότροφος και μετά ως τακτικός αστρονόμος προσωπικού. Καθώς η έρευνά του αφορούσε πάντα τα αστέρια που πεθαίνουν, ήταν σε αυτό το Ινστιτούτο Max Planck στη Βόνη που άρχισε να εργάζεται με στόχο να αποκτήσει καθαρή άποψη για αυτά. Το 2014 μετακόμισε στη Χιλή. Επί του παρόντος είναι αναπληρωτής καθηγητής στο Ινστιτούτο Αστροφυσικής στο Universidad Andrés Bello στο Σαντιάγο και συνεχίζει να επιδιώκει τη λήψη μεγεθυμένων εικόνων των αστεριών που πεθαίνουν προκειμένου να αντιληφθεί τι συμβαίνει πριν από τον αστρικό του θάνατο. Στην απόψινή συζήτηση θα με συνδράμει με τις εξειδικευμένες γνώσεις του ο αγαπημένος φίλος και συνεργάτης Μανώλης Αγγελάκης, διδάκτορ εξωγαλαξιακής φυσικής, ο οποίος βρίσκεται στη Βόνη. Αγαπητέ Μανώλη, χαίρομαι που είσαι και πάλι εδώ και θα κάνουμε την εκπομπή μαζί. Μανώλη, μ' ακούς?
Η χαρά είναι δικιά μου, Σπύρο.
Καλησπέρα. Ο δόκτωρ Μανώλης Αγγελάκης γεννήθηκε και μεγάλωσε στην Ιεράπετρα. Σπούδασε φυσική στο Αριστοτέλειο Πανεπιστήμιο, ενώ για την διπλωματική του έρευνα εργάστηκε στο Jodrell Bank Observatory του Ηνωμένου Βασιλείου. Μετά τις σπουδές του εργάστηκε στο Northwestern University, στο Evanston του Illinois, τον ΗΠΑ, ως προδιδακτορικός ερευνητής. Αργότερα ξεκίνησε τη διδακτορική του διατριβή στο Ινστιτούτο Max Planck for Radio Astronomy στη Βόνη και στο Πανεπιστήμιο της Βόνης. Εργάστηκε στο Max Planck αρχικά ως μεταδιδακτορικός ερευνητής και μετέπειτα ως βασικός ερευνητής. Για το διάστημα 2009 έως 2015 υπήρξε ο επιστημονικός συντονιστής του International Max Planck Research School for Astronomy and Astrophysics. Έχει ασχοληθεί κυρίως με την ραδιοφυσική pulsars, ενεργών γαλαξιών και ειδικά της κλάσης blazars, μέσω της ανάλυσης πολυσυχνοτικών χρονοσυρών, καθώς και με παρατηρησιακή κοσμολογία. Το μεγάλο πάθος του είναι η εξωγαλαξιακή φυσική των πιδάκων πλάσματος μέσω πολυσυχνοτικής πολλοσυμμετρίας. Ο Μανώλης Αγγελάκης στο διάστημα 2014-2018 υπήρξε αντιπρόεδρος της Ευρωπαϊκής Αστρονομικής Εταιρείας και από το 2018 έως το 2020 γραμματέας της. Το 2022 εξελέγει στη θέση του επίκουρου καθηγητή παρατηρησιακής αστροφυσικής στο Πανεπιστήμιο Αθηνών, που για προσωπικούς λόγους αδυνάτησε να αναλάβει. Και το γνωστό μήνυμα στους τακτικούς κυβερνοθεατές μας της εκπομπής. Όπως γνωρίζουν οι φίλοι της εκπομπής, τα φυσικά είναι μια εθελοντική δράση, από την οποία αποκομίζουμε ως μόνο όφελος τη χαρά των συζητήσεων με ουσιαστικούς ανθρώπους και την ευχάριστη αίσθηση πως μας παρακολουθεί ένα σημαντικό σε αριθμό και ποιότητα κοινό. Γι' αυτό το λόγο, πριν προχωρήσουμε, επιτρέψτε με να σας υπενθυμίσω να πατήσετε «Μ' αρέσει» στο YouTube είτε στο Facebook, αναλόγως από πού μας παρακολουθείτε. Επιπλέον, θα ήθελα να παρακαλέσω όσους μας παρακολουθούν από κανάλι του YouTube και δεν έχουν εγγραφεί ακόμη, ας το πράξουν κάνοντας κλικ στο πλήκτρο εγγραφή και στο καμπανάκι που θα εμφανιστεί, προκειμένου να ενημερώνονται αυτόματα για τις νέες εκπομπές μας. Όπως ίσως γνωρίζετε, συγγνώμη, μισό λεπτό παρακαλώ. Πολλοί και πολλές από εσάς, η σημερινή μετάδοση γίνεται στη θέση της εκπομπής μας της περασμένης Παρασκευής 21 Φεβρουαρίου, η οποία για πρώτη φορά στα 5 χρόνια που είμαστε στον αέρα, διακόπηκε νωρίς λόγω σοβαρού τεχνικού προβλήματος στον ήχο. Αφού ζητήσουμε για μια ακόμα φορά συγγνώμη από τους φίλους και τις φίλες που ταλαιπωρήσαμε την προηγούμενη φορά, δηλώνουμε πως εργαστήκαμε εντατικά για την αντιμετώπιση του και όλα δείχνουν πως αυτή τη φορά θα απολαύσετε ένα σπουδαίο θέμα χωρίς προβλήματα. Επειδή η εκπομπή είναι στην αγγλική γλώσσα, αναγκαστήκαμε να γράψουμε το κυρίως μέρος της σε βίντεο εκ των προτέρων, προκειμένου να προσθέσουμε ελληνικούς υποτίτλους. Βεβαίως, ο κύριος Ονάκα θα παραμείνει μαζί μας, προκειμένου να παρακολουθήσει το βίντεο και να απαντήσει σε ερωτήσεις του κοινού μας μετά την προβολή του, ώστε να γίνει διάλογος με τη δική σας υποστήριξη όσον αφορά με τη δική μας υποστήριξη, του Μανώλη και εμού δηλαδή, όσον αφορά στην ταυτόχρονη ερμηνεία.
So, on the 21st of November, so end of the year that just turned, there was a press release from the European Southern Observatory that attracted the attention of all of us. And I'm reading from that publication of the ESO. For the first time, we've succeeded in taking a zoomed-in image of a dying star in a galaxy outside our own Milky Way, which is already catching a surprise. And then later I'm reading that we discovered an egg-shaped cocoon closely surrounded the star. And finally, we are excited because this may be related to the drastic rejection of material from a dying star before supernova explosion. So Keiichi, first of all, I also wish to wholeheartedly welcome you to this show after not having you for so many years. And I think that tonight there is a lot to unpack. Already the first paragraph of the press release was absolutely attracting your attention, and there is a lot to unpack. So the first question that I would like to start with would be, what was exactly that made it to the news? What was exactly the discovery that pushed ESO to publish such a press release?
Well, first of all, as the title said, it was the first zoomed in or close-up image of an individual star outside our galaxy, outside Milky Way. And this is quite difficult. It is, first of all, technically difficult because the star is actually quite big, much larger than the sun. But the distance, and then the star is not in our Milky Way galaxy, but in another galaxy called Large Magellanic Cloud, which you cannot see from Greece. Unfortunately, you have to go to the southern hemisphere, for example, in Chile, where I am. And anyway, so the distance to this neighboring galaxy, Large Magellanic Cloud, is some 160,000 light years. So it's the distance is so great that it's beyond the imagination. It's hard to imagine how great the distance is, 160,000 light years. But it's so far away, so then the star looks so small, and this is the challenge. And so that you can have some idea how small this star called WOH G64 looks like. I mean, this WOH G64, this star has no other fancy name like Betelgeuse or Antares. It's just the catalog name, unfortunately. And so that you can have an idea how small it looks. You can imagine that for example, so can you imagine? So this is the map of Europe. Do you see that?
Yes.
Yeah.
And then, for example, here
it is in Greek.
Yes, exactly. Yes. This is the Google map. This is the Google map, and then the Google map has a very nice function to change the language.
Yeah.
So this is the map of Europe, and Thessaloniki, where you are sitting, is here. And now, for example, here is Paris in France.
Right.
And in Paris is Eiffel Tower. It's a very famous tower. Okay, and then you can imagine that that ping pong ball, a ball for ping pong.
Yes.
Of this size, and you put a ping pong ball at the top of Eiffel's tower like this. Okay, it looks very big. It looks like huge balloon, but you have to imagine that what we really put on at the top of Eiffel Tower is just a real ping pong ball of this size. Okay. And now you are sitting in Thessaloniki, so we put a telescope and we observe this ping pong ball at the top of Eiffel Tower in Paris from Thessaloniki. And this, and then you imagine that the ping pong ball looks super, super, super small. And the WOH G64 in the Large Magnetic Cloud looks as small as a ping pong ball at the top of Eiffel Tower, seen from Thessaloniki.
Oh.
This is breathtaking to realize the advancements of the technology that are necessary for such observations of what you just said. So we definitely got a very clear impression from all the things that you told us about the physical dimensions that are involved. One of the very first things, because I know to much extent the work that you have been doing when we were together in Bonn, and also the group that hosted you from Professor Weigel here in Bonn. I have actually, one of the first things I thought when I read the press release was whether this has been an accidental discovery from your side, or whether this was actually something that you were after. And if this was something that you were after, how would it have been chosen, etc., etc. So share some thoughts and share some insights with us on this.
Yes, so actually the WOH G64, although the name is very, although it has no fancy name, its proper name, but it's a very extreme object in a sense that it is ejecting its material at such a tremendous rate. And it is a dying heavyweight star. And therefore, it is one of the brightest stars in the Large Magnetic Cloud if we observe in the infrared light. And I will show the...
Is it correct to say that if you bring this star in the place of our sun, then it will occupy a part of our solar system up to Saturn?
Yes. I will show this. All right, so to have an idea how big the star is, okay, I said the star looks as small as a ping pong ball on the top of the Eiffel Tower, seen from Thessaloniki. But so it only looks small. The real size of the star, WOH G64, is huge. So this is a very schematic, picture of a solar system. Here at the center, there is a very small orange dot, which is the sun. And this very small circle is the orbit of the Earth. And then this one is the orbit of the orbit of Saturn, and this is the orbit of Neptune. So basically, this is Neptune is the outermost planet of the solar system, because Pluto is not a planet anymore. So if we put as Spiro said, if we put WOH G64 at the place of the sun, it looks like this.
Oh.
So it's quite big.
Well, we definitely have an impression of the size of the star in reality. Yeah.
Yes. And now let's go back to the question of Manolis. So the WOH G64 is a really huge giant star, dying heavyweight star, and ejecting material at such a tremendous rate. And it's very bright. So although the distance is quite great, if the object is bright, it's easier to observe. And then it's such an extreme, unique object that is losing its material extremely. So that's why this star has been catching our attention. And actually, this is not the first time for us to observe this star WOH G64 at high resolving power. Back in 2005 and 2007, we observed this star with the same facility at European Southern Observatory in northern Chile. And at that time, we already measured the size of the star. But at that time, we didn't have an image, but only the measurement of the size, meaning how big the star looks, right? And then because we didn't have an image, we used the data, and then we made a computer model. And then the computer model said, well, the star is not just surrounded by, say, round shell, but it has a big donut. I will show this. So again, this is not an image we took at that time. And then it was the image artist impression. Made when we made the press release from the European Southern Observatory. So here at the center, there is a star, and this star is the gigantic star which fills up to the orbit of Saturn. Okay, and then surrounded, this is already the size of this white spot. This is already the size of Saturn. And then surrounded with a huge donut. And this is what our computer model said based on the data. But at this time, the European Southern Observatory had the first generation instrument of the so-called Very Large Telescope Interferometer, some special facility infrastructure to do to close up or zoomed in observations. We could measure the size, but not the image. And so actually we were waiting for the next generation, second generation instrument that enable us to take a real image and to see if our computer model is correct or not.
Okay. Let me try to wrap up for the general public. So in 2005-2007, already using techniques, the interferometric techniques like you use today, you would get a constraint of the size. That means you could get a sense of how big the star is. And then understanding a little bit the physics and understanding a little bit the dynamics of the environment, the picture that you just showed us is what it should look like for these constraints of size and for these physical processes in the close vicinity of the sun. I suspect that during our discussion tonight, later we're gonna at some point say that, well, this was the artist's impression according to the measurements that the poor, if I can say, measurements that we had in 2005, which have been confirmed with a much higher resolution, and the image that you got at the end of 2004 that was published recently, confirming this artist's impression, if you like. Good. So the answer to my question is, obviously, that was not an accidental observation. It was not something that, for example, it became bright, it attracted the attention, etc. It was something that has been targeted, has been followed for the several past decades or so, or a couple of decades. And this observation is a result of a persistent, systematic attempt to learn something about this really, truly exotic environment, such as a giant star out of a different galaxy. So I, from my professional standpoint, I suspect a number of reasons why such systems are interesting, and I'm sure that there are even many more. So my question is, do we have such close images of stars in our own galaxy or in other galaxies? Not in other galaxies, this is the first time, in our own galaxy at least.
Yes, I would say the astronomers have taken close-up images of the surface of stars other than the sun, like 20 or a little more than 20 stars. Thanks to the advance of the technique to get high resolving power or zoomed-in images. And maybe I should show an example.
Yes.
For example, this one. So this is a very nice astrophotography, Milky Way, and this is one of the VLTI telescopes here. And then this is the constellation Scorpion. This is the head, and this is the tail of the scorpion. And this bright star is received the very gigantic star called Antares. You can see that this star, you can see it from Greece if the night is dark enough. And then it was 2017, we published the image of the surface of Antares with the best resolving power, or the best close-up image, which looked like this. And so this is the surface of this gigantic star, Antares, and you can see some bright spots or bright regions. And this fluffy thing is the atmosphere of this star. And this is one of the images. And then the images like this, maybe a little, little lower resolving power or less close-up images, but we have about 20 or a little more than 20 images of stars other than the sun.
Okay, good. Do you want to spare a few words the technique and the specific arrangement of the observing apparatus that you use for these observations, Keiichi? Because I know, but I think it's interesting for everyone how challenging, how difficult, how precise this implementation is, how expensive because of all these reasons. So do you want to share a few about what is actually the specific apparatus that you use for the telescope, the facility that was, and what is the novel technique that is utilizing such high and high resolution images, so that would be the equivalent of seeing a ball on the top of the Eiffel Tower from the summit?
Yeah. Okay. So to have such a high zoom-in power, we need a very big telescope, because the bigger the telescope is, or basically the telescope is a mirror. Bigger the telescope is, the better or the higher the sharpness, or the sharper is the image, or the higher the resolving power, or the zooming power. Okay, so now, for example, to take an image of this star WOH G64 in another galaxy, or the ping pong ball at the top of Eiffel Tower, seen from Thessaloniki, we will need a telescope larger than 100 meters. It means we will need a mirror larger than 100 meters, its diameter. And to make such a gigantic telescope with a 100-meter mirror or more than that will be very, well, first of all, it doesn't exist. And to construct such a gigantic telescope with a 100-meter diameter mirror will be very difficult and very expensive. So instead of constructing such a gigantic mirror, we combined 4 telescopes. And then each telescope is not so big, just 1.8 meter in diameter. But if we combine the light collected from 4 telescopes and process it in a proper way, in a special way called interferometry, then we can get resolving power or zooming power equivalent to the separation of the telescopes. So I will show the facility I used.
That would be very helpful. Many of conspiracies show observers are observers themselves. They will very follow what you say.
So this is the aerial view of the Paranal Observatory of the European Southern Observatory, which is in the northern Chile. It's about a little more than 1,000 kilometers from the capital, Santiago. Now you can see some telescope for 8-meter telescopes, and this is another telescope. Now, another aerial view is like this. So they have here 4 8-meter telescope. You can not see the mirror, but you can see the domes. And then there are 4 small telescopes here, 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 and here. And then we combine the light collected by those 4 telescopes and process in a special way. Then, in that case, for example, we can have a virtual patched-up telescope of this size. Each telescope is small, just 1.8 meters, but if we combine them, if they work them together in a special way, then you can imagine that we have a telescope as big as this.
Are they movable?
Yes,
The little
I will
ones.
show. Yes, I will show you. And then in this case, for example, the separation from here to here is like a little more than 100 meters. In this way, we can have a virtual patched-up 100-meter telescope, and this is exactly what we need to have the zooming power to get an image of WOH G64. And these 4 big telescopes fixed, of course, but these 4 small telescopes can be relocated, okay, like this.
Huh.
So what they do is they jerk up a telescope, and then there are, maybe you can see that here, there are rails, like train. And then along the rail, for example, this telescope is jerked up, and then along the rail, it's moved to a different location, as you can see here. So in this way, we can have a virtual 130-meter telescope. And then in our case, the largest separation was 130 meters. So that's why we had a virtual 130-meter telescope, and that gave us the resolving power, the zooming power.
Necessary for resolving such a distant object. Of course,
Exactly.
The interferometer is equivalent with a 100-meter telescope or so in terms of resolving power.
Yes.
For sensitivity, of course, one would need a larger collecting area, but that's just a technical detail which I mentioned only.
Yes. Yes. So this is when we observed WOH G64 back in 2005 and 2007, they could combine only 2 telescopes. We used the instrument that combined only 2 telescopes, and that's why we couldn't make an image. Now we use the 2nd generation instrument called gravity, which combines 4 telescopes. And that is the key to make an image. And also, as Manolis touched, it's the star is not bright. Okay, this is the brightest star in the infrared light in the large magnetic cloud, but still it looks so weak. So therefore, well, you can again the comparison to the ping pong ball in France. Okay, ping pong ball at the top of Eiffel Tower, seen from Thessaloniki. But now you have to imagine that it's at night, dark, and this ping pong ball on Eiffel Tower is only really, really weakly illuminated. It's not the light. It's not emitting strong light like a lighthouse, but only maybe like a candle, really weak. And you want to see it from Thessaloniki and take a photo. This is the challenge.
This is truly challenging.
Yes, and then the 2nd generation instrument gravity is exactly the instrument that make it possible.
Well, let me take the opportunity to ask here. Also, I am an observer by training, and I know how hard it is. I wonder what was the most challenging data pre-processing step that you had to take, because I assume that every source of noise, especially because you have been observing in the infrared band of the spectrum, every source of noise must have been extremely challenged to overcome. So what was the major difficulty you had to bring the data to a quality which would be good for science?
Yes, so the point is, with this technique called interferometry, we do not shoot a direct image like this.
Yeah.
But we measure some data, and then later we process the data and reconstruct or restore the original image. And this restoration process is the complicated thing. And I guess the greatest challenge for me was to check and to be sure if we see what we see in the restored image is really true, or maybe just say just some errors. Artifacts, not real things, simply coming from or resulting from some problem in the data processing or in the restoration process. And so in the end, I will show this image that we obtained.
Yes, and we will need that to focus a little bit on this anyhow.
Yes. Oh, so maybe I will start this, and this is because maybe the audience in Greece might not have seen the large magnetic cloud. Well, you have to, even in Chile, you have to go to places with dark sky. In Santiago, where I cannot see it. So this is the large magnetic cloud. It looks like, with the naked eye, it looks like a very diffuse cloud. So that's why it's called large magnetic cloud. And this is the small magnetic cloud. And this is the large magnetic cloud, but see in infrared light. And this is our star, WOH G64.
Mm-hmm.
And this is the image from the press release. And in the end, guys, what we see is this thing, like an egg, and this ring, a larger ring. And in the end, we are sure that this egg is real.
So
it's not
the surrounding rings, the donut-like shape, is an artifact of the technique?
We cannot exclude that possibility, but we probably real. And to confirm this ring is really real, we need more data.
Right.
What was the volume of the data you processed?
Not so much. I don't remember how many gigabytes it was, but the original data of the size of, I don't know, maybe 10, 20 gigabytes. And then after the data processing, it goes very, very small.
Yeah.
And then for the restoration, and then the image restoration process is done with this the reduced data, not the 10 or 20 gigabytes data. So the data side is not a problem.
Keiichi, how many observing hours did you need for this, and over what period of how many days was it spread?
2 nights.
2 nights only.
2 nights, but 2 full nights, because I will show this again. This the observatory, and on one night we had a telescope configuration or telescope positions very wide. I mean, this means the first night the telescopes were located wide apart, maybe like this. Not exactly like this, but the separations were quite large on one night. And then several nights later, maybe 1 week later, we observed the same star during a full night. But then the telescope configuration was much smaller. This means the telescopes were positioned like here, another one here, here, and here. So very compact.
Yes.
Configuration. So this was necessary to have a reliable restoration process of the image.
So I assume for our viewers that in the first night you use an expanded configuration so that you could get the fine details, and then you brought the telescopes together in a compact configuration, which of course would also result in much lower angular resolution. So the zooming power would be much smaller, but it would also be able then in that configuration to detect more diffuse regions of emission. Is that the reason?
Exactly.
Yeah.
Exactly. Yes.
And then you
Because
can get a more complete image of reality.
Exactly. Yes. Exactly. So because the before our observation, we didn't know so much about the object, what the object looks like. Well, we had a computer model, but which might have been completely wrong. So as Manoli said, we wanted to have this very wide configuration, very large configuration of the telescope to see details, to capture details, and also very compact configuration to see something diffuse, because we didn't know that.
So in a sense, this is even more impressive now that we talk and we start to unpack all this. This is even more impressive, the whole story, because you realize that you are going after something for which you have very high uncertainty of what you're going to find. Because all you have in your hands is an estimate of the size and a computer model that tells you how it will look, but you have no certainty at all. And given the very power of the source itself and how dim it is and how far it is, and also that it's dynamic, so it may have changed since 2007 when the simulations were, you really are very uncertain about what you're going to find. But in the end of the day, with only 2 nights of observations, you got a smashing result. This is really, it's really an impressive result on its own sake. So I wanted to take this a bit further. If we focus on the image that that you managed to acquire, having in mind, let's say, what we can understand for this system, for this environment, for this cosmic environment, if you like, what is that you should ask an unexperienced spectator like us, that we are viewing the show tonight, to pay attention in the image? So what is, in your opinion, as a professional astrophysicist, very deep into the system, the features that we see in the image that can tell us something about the physics and the processes that they take place there?
Okay, so then I will show this image again. So the egg, this egg-shaped cocoon, and I think this is material ejected from the star, because the star itself, although it fills up to the orbit of Saturn, it's very small in this image. So it probably is hidden in the cocoon at the center here, but we don't see it. And what we see I want the audience to understand that this cocoon, this egg-shaped cocoon, is not the star. It's not it's not a star like a rugby ball, but it's just a material ejected from the star. And what's important is it doesn't look like a donut. Okay, maybe this ring can be the rim of the donut hole. So I will show maybe I will explain better with the camera. So
did you pause?
This is donut.
Yes.
And we thought the center star is here, and then we are seeing like this star and like this, okay? And then this is our computer model set based on our previous measurement data. And this was depicted in the artist's impression in ESO press release from 2008. Okay, and what I want to say is this part of donut. Okay, this part of donut, and then we have the star here. We have a star, and then the star, of course, emits the light. So this part of the donut hole is heated by the star directly, because this part of the donut hole receives the starlight directly. It's heated up and it emits infrared light. And this is what we see as the ring. Okay, so why don't we see the rest of donut? Because the rest of the donut is too cool to emit this infrared light.
All right.
So now, but then our donut model did not predict this egg-shaped cocoon. Let me put the donut away. And okay, so then we thought, okay, we think this is the material from the star, ejected from the star, but not predicted by our previous donut model. And then what is wrong? Maybe our donut model was completely wrong. And then we found out that we looked up some data, because this star is quite famous. So there are some the measurement of the brightness. So measure the brightness is much easier than taking an image. So there are many measurements of the brightness, and we found that the star has become much fainter than before, than when we observed the star for the first time back in 2005 and 2007. So that's why the thing is, in the meantime, in the last decade, probably the star has changed, has been evolving somehow. And then at some point, we think the star started to eject more material. And this this egg-shaped cocoon is the consequence of this ejection of material, more say higher ejection of material. And so this is the case, not just the image, but also this the evolution in the last decade is one of the discoveries.
So, in fact, from what you're saying, and that's also very clearly communicated in the press release and in the publication that you made, is that the system is dynamic. So this is another thing that later we're gonna also emphasize a bit more, is that not only is that a dying star, not only is that a direct image of a dying star in another galaxy, but it's one of the very few cosmic phenomena and systems that not even in a lifetime's period we can observe its evolution even shorter than that. So within a decade we see the thing changing, which shows already how dynamic it is. Just to cast a misunderstanding, Keiichi, the image that we are seeing is not real core, it's a fake core, obviously, right?
That's right, yes. So this is we observe infrared light. And just to understand, I don't know if I guess many people have heard of infrared light, but what it's good for. And to make this point, I prepared a slide. Here, this one. Okay, so this is a guy with his hands in a black plastic bag, and this is normal photo, normal image. With it, this means a photo taken in light that we see. It's called visible light. Now we should we shoot the same object, this man and this man, in infrared light. It looks like this. We can see his hands in the plastic bag. Now we cannot see his eye, but just glasses, dark, like sunglasses. But obviously, it doesn't have sunglasses on, just normal glasses. So the thing is, it's thermography. Maybe some people have heard of thermography. This means with thermography, we can measure the infrared light emitted from warm things. Therefore, for example, here, his face is warm, so it looks very bright in infrared light. But here, why glasses look dark? Because the glasses blocks the heat from his eyes. That's why it looks dark. And then in the infrared light, you can see through this black plastic bag and see the hands, because his hands are warm and emit infrared light. So the point is, if we observe, for example, stars or galaxies in infrared light, we can see and we can investigate different things. Or we can, for example, see through some material blocking the usual visible light. And the infrared light we cannot see with our eyes. Therefore, the image we took is in the infrared light. So basically, we cannot put any color. But then why this color? Because it looks warm. It can be blue or it can be violet, as you like.
Yeah.
Or it can be rainbow. It's a matter of taste.
It's always so impressive to see in reality how different perception of the universe one gets just observing at a different wavelength. And now we're talking about infrared, which is not that different from the usual wavelengths that our eyes are using. So it's are detecting. So it's really impressive to see how different the impression you can have is. One thing that you implied, you didn't specifically say that, but I would like some clarification into that. Is it, did I understand correctly that you have an impression or an estimate of the inclination of the whole structure towards the observer? And if that is the case, how has that been achieved? Or was that a misunderstanding from my side?
At the moment, no. Because okay, so let's go back
I
to
asked
this
that
image.
to show the donut, and you implied that it's a little bit inclined towards us.
Yeah.
But I guess one answer would be that you judge that from the geometry that you see.
Yes. So if we think if this ring is really real, not artifact or error from the restoration process, then we can. I will make a donut again. We can see, of course, we are not seeing the donuts like this, probably like this from you. And then you can see then the donuts. Basically, donut is circular like a ring, but then it looks like a bit compressed.
Yes.
And with this, you can estimate the angle. But I guess we should do that once we are sure that this ring is real. And now, yes.
I want to ask you why egg-shaped and not spherical?
Yes, it's a good question, and this is exactly what I wanted to say. And now this egg is not round because the star itself should be more or less round, but it's like this, egg-shaped, and we think it is because of unseen companion star inside the cocoon. So what we think is two scenarios. This is also related to the angle, the viewing angle, that Manolis mentioned. So in one of the hypotheses, again, I need a donut. And then egg can be like this. So this is, okay, it's a pencil. It's not an egg. But then you have to understand this part of is like this, the egg-shaped cocoon, long cocoon. And then it is like this, and then you see it like this.
Mm-hmm.
So this is the egg-shaped cocoon, right? So, well, then you can see the donut, and then inside something long. Okay,
Yes.
this is one hypothesis.
Mm-hmm.
And then in that case, or this is even more difficult. So the other, sorry, donut has so much sugar. So so we have donut like this, and then inside donut, maybe there is this egg-shaped cocoon is like this. But in this case, in the first case, the cocoon was like this, perpendicular. This is donut, and then the cocoon was like this in the first hypothesis. Now in the second hypothesis, cocoon is like this. Again, well, we can see the same thing. If the donut is like this, the cocoon is in the plane of donut, and then you can see like this, and then basically you have the same appearance.
Mm-hmm.
And in both cases, we think this star has an unseen companion star, and then the interaction between two stars can make the spherical round things to egg-shaped cocoon. So in the first scenario, maybe because of interaction, material is ejected only in this direction and in this direction, in the direction of the North Pole and from the South Pole. In the second case, maybe we have the gigantic star and its unseen companion, and then because of interaction, this round cocoon is deformed like this, because the companion is here. The companion star is here. But at the moment we cannot distinguish two scenarios.
Yeah. Yes. And I was thinking that a very typical question in second year astrophysics in the physics department in Greece, a very typical problem that is given is whether you would be able to see, for example, from a very far distance, whether you could discriminate Jupiter and the Sun. And the long story cut short is that, of course, if you're observing visual light, where you have a star or sun dominating the sky, you won't see anything else because you're about to be overshined. But if you were shifting your observing band pass towards the infrared, where the Jupiter this time is dominating because the star, our sun, is very, very hot and the Jupiter is much colder, the Jupiter would dominate and you would actually be able to resolve it. So if this scenario, if you were after answering the scenario of a companion star, would such an observation help you?
Yes, the different observing at different wavelengths.
Exactly.
Yes. So as I said, actually the thing is, we wanted to observe this star WOH G64 at longer wavelengths. There's this infrared light, but another type of infrared light. So the infrared light more sensitive to colder material, to see the entire donut, not just the only the donut hole, but the entire donut. And then it was not possible. It was unsuccessful. Then the first year, after this observation, we observed that, and then it was successful. And then, but we had bad weather. So we went back, we submitted a proposal, approved again, and then we wanted to observe, but then it was unsuccessful because it had become too faint. And then I thought, okay, the star is changing, and then we started to monitor the brightness without taking an image, just to monitor and measure the brightness every month. And then so far, the star is getting fainter and fainter. And maybe I can show you the example of the data. So this is WOH G64. And this was the image taken in October 2023, so more than a year ago. And then this is the image taken in December last year, 2024. So this is October 2023, December 2024. So this star, for example, this star hasn't changed its brightness, but obviously WOH G64 here has become fainter.
Yes.
This now. So the star is getting fainter and fainter. And therefore, because I think the material in the cocoon ejected from the star and the material in the cocoon is blocking the starlight. It's not that the star is disappearing. The star is still there. So maybe I will go back to the image.
That makes it even more interesting. Yet another
So
complexity.
again, so this is the image in visible light.
Yeah.
It's fainter, but then it's not, the star is not disappearing, because if we take an image in infrared light, it's very bright, still there. So the star is not disappearing. It's just that it appears to be fainter because I think the material in the cocoon more material is blocking the starlight. So then maybe we can take advantage of this natural, say, sunglass. And for example, it might be interesting to observe the target in ultraviolet light. Because if we go to infrared light, the star is bright, as we have seen. The star is getting fainter and fainter in visible light, but still very bright in infrared. So as far as you are observing this object in infrared light, you only see the bright star, not its companion. But if you go to blue light or ultraviolet light, there the star is very faint.
Yeah.
Intrinsically very faint, and now thanks to this the blocking of the material, blocking due to the material, it appears to be even fainter. And then if the companion star is a hot star, maybe this companion star can outshine the red supergiant star.
Yeah.
And we can see this.
Okay, this is really very interesting. This is exciting, more than interesting. And I'm going to pick up on the supergiant terminology that you use, but I'm going to put a pause. I can't help asking you a couple of questions. Spiros knows that very well, how obsessed I am with understanding or getting a sense of the physical conditions at the cosmic environments. So I have two questions which I have not planned, but they came naturally. We have been saying that generally because by definition you have been able to observe in the infrared light because the material is generally colder. So first of all, I would like to have a sense of the temperatures that we are talking about this material. We say colder, but in astrophysics cold can have a very different meaning.
Okay, so first of all, the temperature of the star, the surface temperature of the star. This is the star, the gigantic star that fills up to the orbit of Saturn. This is about 3,000 to a bit around 3,000 degrees. And I know this is really hot for us, for humans, but in astronomy they are called cool stars.
Yeah.
So 3,000
compared to 6,000 degrees.
Exactly. So
surface of our sun.
Yeah, exactly. So sun, and then there are say hotter stars than the sun.
Yes.
So this star with the surface temperature of 3,000 degrees, it is a cool star.
Okay.
Now,
so that's
the cocoon is the material in the cocoon is a little far away from the star. So therefore, I guess their temperature is like 1,000 degrees.
Much lower.
Lower, but still hot.
And of course, and then it takes me, but you won't necessarily feel that hot because of other reasons. So that takes me to the next question that I had not planned, but I can't help asking, which is the composition and how would you feel if you could touch the surrounding, the dust, especially that you said. You mentioned very often the dust, which is one of the materials that form this embracing structure. So what is the dust made of? What is this material made of?
Yes, so in astronomy, dust is not just a house dust, but basically you can imagine it's like a sand grains. Sand grains, but much smaller. You can see the sand grains, but usually the grains around in the universe can be much smaller, like smaller than 1 micron. 1 micron is 10,000 is 1,000 times smaller than 1 millimeter. So very fine sand grains, or in other stars, not WGG64, in other stars, it can be soot, like black smoke. It is very black carbon grains. And this kind of material, or it can be like crystals. But again, crystals are different minerals, but then again, they are much smaller than, for example, than a crystal that we usually see on the Earth.
So, as a matter of fact, the terminology dust is not that far from what we intuitively understand when we hear the word dust. Good.
Yeah.
So now let me change completely the quality of the questions and move on to something that will help us a little bit understand the physics of this exotic system itself. You mentioned repeatedly the terminology supergiant. So, this is one of the different possible final stages of evolution of a star, which depends on whatever parameters they have. So tell us a little bit, Keiichi, if you like, a little bit about the supergiant, what is the characteristic, and then I will read something from the press release, which has a lot. Please. So I'm reading. Let me do that first, actually. So I'm reading from Professor Weigelt when he was interviewed by the press release journalist. We have found that the star has been experiencing a significant change in the last 10 years, which you told us again and again in the most descriptive fashion. And he continues, providing us with a rare opportunity to witness a star's life in real time. We also said that in 10 years, in just a part of your own career, you have seen the star actually significantly changing. And then he continues, in their final stages, those stars, the red supergiants, like the one that you have observed, the outer layers of gas and dust in the process, are ejected in a process that can be last thousands of years. This star is one of the most extreme of its kind, and any drastic change may bring it closer to an explosive end. Now, all this is full of excitement, right? So tell us a little bit about the supergiant, the explosive end that it may have, when it's going to end it, what will be the evolution path to be expected?
Mm-hmm. Okay, so it's about the stars, 8 or 9 heavier than the sun, but more than 8 or 9 times heavier than the sun. And then at the end of their life, they enter the so-called red supergiant. So why is red and what is supergiant? First of all, the star expands, so the star is really blown up. It's really bloated.
So it's becoming a giant.
And then so then not giant but supergiant.
Supergiant.
Right. At the same time, the surface temperature goes down. At the beginning, maybe it was like more than 10,000 degrees, or maybe 20,000 degrees. And now, when they enter the red supergiant stage, they expand, and then the consequence is the surface temperature goes down to 3,000 degrees. Okay, it's still hot, but much cooler than 10 or 20,000 degrees. So that's why it's called red supergiant. And basically, those bloated cool stars are in the final stage of their life. And then we astronomers think after a while, at some point, they explode. Explode means all the material, all the stellar material is somehow kicked out, like in an explosion like this. And actually that happened back in 1987 in the Large Magellanic Cloud. And I have an image. So I think this is so far one of the most famous supernovae, supernovae SN 1987A. So it is one of the, it is in the same Large Magellanic Cloud as WOH G64, but a different star. Okay, here there was a star, and one day in February 1987, it exploded. And the supernova explosion, when a star explodes in a supernova explosion, it becomes much, much brighter. I'd say 100 times brighter than the original star within a day or so. And it can outshine, it can be the single supernova can be as bright as or maybe brighter than the entire galaxy. And then over a year or so, it becomes fainter and fainter and fainter. So this is the supernova. And this is the end. This is the end of a star.
Mm-hmm.
So the death of the star.
Okay. Mm-hmm. What are the processes on the surface of those dying stars that can last thousands of years?
Yeah. So this is yes, in the red supergiant stage, the star is, say, ejecting the material. Okay. But you can imagine that the star blows up like this. And then this is, say, so, but then this means this material, the star, is very, very, the outer layers are very, very fluffy. Density is very low and then very tenuous.
Mm-hmm.
Still, you have to think at the center, there is a star. In the case of WOH G64, 25 times heavier than the sun. So in principle, the gravity of this star 25 times heavier than the sun keeps the material. Nevertheless, keeps the material from flying away. But nevertheless, we know, astronomers know that red supergiants are ejecting material. This means the material in this fluffy outer part of the star somehow manages to escape the gravity of the star and go back to the interstellar space.
Mhm.
We know this phenomenon, we just don't know how it occurs. How the material, this tenuous material, manages to escape the star, because something must be pushing, some force must be given a push to the material so that it can go away. But we astronomers still don't know exactly what the force is.
So even if you don't know exactly the mechanism that empowers this evolution, do we at least have an experience or an estimate of how fast it's happening? So if, again, in human terms, would we be able to see this evolving? And if yes, how fast would it be evolving?
It's a good question. Usually it's like 1,000 years, maybe 10,000 years. So in that case, the time scale is much longer than human time scale. But recently, the astronomers working on supernovae found out because those people are working on supernovae, and now they found out the stars before the explosion. These are the red supergiant stars before the explosion were ejecting material such a tremendous rate, and some say it was like 10 or few years or 10 years just before the explosion.
Okay.
So this means it depends on who you ask. But some say just a few years before the explosion. Some say maybe 10 years before the explosion, or maybe 100 years before explosion. But in any case, it's a human time scale.
Okay. So,
and in this case, we might be able to see something in real time.
Okay. So with all this, one understands that there may be an estimate of when this particular star is going to explode. And right? So when do you think? I guess you do have some estimates of when it's going to explode.
No, unfortunately not. Well,
Okay.
I would only say maybe in the next several thousand years, or within 10,000 years. Okay, so if I give a large number, it's safer.
Okay. So no chance that one of us will observe it.
Yeah, well, we don't know, because the point is we know that those heavyweight stars explode at the end.
Yeah.
But astronomers have not yet understood what triggers the explosion. So it's hard to predict.
Now, another thing that I've been thinking since I read the press release from the beginning was the following. We know that the evolution of the stars is not independent of the environments that they are living, and vice versa. We know that the life evolution that the different stars take influence the life of the stars in the vicinity. So my question is the fact that this particular system is actually living on the Magellanic Cloud, whether that has something to do with its evolution, if you have any such evidences that the evolution is triggered or somehow related to the environment it's found.
I don't think so, because this star WOH G64 is not in an area very crowded with stars. So, as you said, if the stars in a very crowded area like a cluster, then interaction with other stars can influence. But I think WOH G64 is still living in relative solitude, maybe with a companion, unseen companion. So therefore, the interaction with other stars is probably not so important for the evolution.
In any case, the suspected or the alleged possibility that there is a companion star will demand an extremely dense environment to have any impact on the star, because the companion star, if it exists, will already have such a much more important gravitational impact on the system than the environment, that the environment could only make a difference if it was very compact after all. Right?
Yeah.
Then that brings me to the final urgent this question that I had planned for tonight's discussion, and that's what is going to be left after the explosion that this star is going to undergo in several thousand years.
Yeah, so probably only the core of the original star.
Mm-hmm.
And then the very compressed, very to extreme high density and with extreme strong gravity. And one is called the neutron stars, a star made of pure neutrons. Very compact and dense and high gravity, or it can be a black hole.
And that all depends, of course, on the material which is available, or majorly on that.
Yes, so basically the mass, how heavy the star is, and or maybe how heavy the star will be at the time of explosion.
Yes. This is all very exciting. I couldn't have wished for any better discussion, Spiros, tonight with Keiichi, that he took so much of his time to prepare for tonight's discussion. While just a few days from his summer holidays, because he's in the South Hemisphere. So I thank you very much, Keiichi, for this. Again, I congratulate you for this achievement. This is groundbreaking, and thank you very much for taking the time to talk with us.
Thank you very much for inviting me to this webinar. It's a very nice and opportunity for me too.
Spiros, the microphone is open.
It was our pleasure to have you here, and Ohayo gozaimasu.
So I should have learned something in Greek.
No. Do you speak any Spanish already, Keiichi?
Yeah, Spanish. Yeah, I do, because I have to give lectures in Spanish.
Oh, you teach in Spanish? Wow.
Yes, that's right. And then supervision of undergraduate students, all in Spanish.
Okay.
And of course, administration people in Spanish. So,
yeah. Excellent. Thank you so very much.
But not Greek. Unfortunately, not Greek.
Next time.
Yeah. Well, you didn't have many Greek students even in the group when you were in Bonn. So.
Yeah.
Good.
Thanks.
Again, thank you very much. This is groundbreaking. This is very important. Thanks for taking the time to share these eye-opening discoveries. And well, I guess we can renew that for the future for another discussion on another exciting topic that Keiichi is working. Keiichi Spiros has been working on many exciting things. So
thank you.
Don't often make it into the news, but yeah.
Also, we'll follow you to see the developments with Gravity Plus.
Yeah, that's right. Yes, it's
That's
really
right.
exciting. Yes,
That's right.
So the renovating the gravity instrument will be even more powerful. This is really exciting. Yes.
Mm-hmm.
Thank you again. Thank you. My microphone. Αγαπητοί φίλοι και αγαπητές φίλες, αυτό ήταν το βίντεο που είχαμε γράψει με τον Keiichi Ohnaka, έναν άνθρωπο ο οποίος έχει κάνει πολύ σπουδαία δουλειά με την ομάδα του βέβαια, και έχοντας στη διάθεσή του όλο αυτό το υπερτηλεσκόπιο, το VLTI, στην έρημο Ατακάμα της Χιλής, του Ευρωπαϊκού Νοτίου Παρατηρητηρίου. Δυστυχώς Ο Κέιιτσι δεν μπορεί να συνδεθεί απόψε, γιατί ο Μέρφυ συνεχίζει να μας χτυπάει. Έχουν διακοπή ρεύματος στην περιοχή τους, πολύ ωραία διακοπή, με αποτέλεσμα να έχουν εξαντληθεί και οι μπαταρίες τους, με αποτέλεσμα όλα τα κινητά να μπαίνουν στο ίντερνετ με data, και δυστυχώς ενώ προσπαθεί και συνδέεται και κάποιες φορές μιλήσαμε μαζί, δεν θα έχουμε τη χαρά να τον έχουμε μαζί μας κατά το κλείσιμο της εκπομπής. Υπάρχουν μερικές ερωτήσεις, τις οποίες... Ναι, Μανώλη.
Συγγνώμη για τη διακοπή. Κατάφερα να μιλήσω με τον Keiichi, τον έχω στο τηλέφωνο. Οπότε, αν θέλεις, μπορούμε να δοκιμάσουμε μια-δυο ερωτήσεις.
Μια-δυο ερωτήσεις. Ωραία.
So, Keiichi, we're going to take a couple of questions just for the sake of it, and the rest I suggest that we answer them offline in a written form. So.
Ωραία. Θα τις βάζω εδώ και θα τις μεταφράζω απευθείας στα αγγλικά, Μανώλη. Πιθανόν είναι καλύτερα να μεταφράζει για να σε ακούει.
Ακριβώς.
Ενώ εμένα πιθανόν δεν με ακούει, ναι.
So, Keiichi, I'm going to start with the first question. So, Mr. Nikitas is asking, the satellites, and in general, all the human constructions that are in orbit around the Earth, are they, I suppose it's a question, do they influence the observations? Or is it because of the focusing to far distant objects, such problems are nulled out? Personally, I can't suspect what is Mr. Nikitas referring to. Maybe you have a better...
Ίσως, Μανώλη, να μας το μεταφέρεις εσύ στα ελληνικά απευθείας.
Ναι, Σπύρο, ναι.
Small field of view, very small.
Yeah.
However, in general, for example, if astronomers want to just the galaxies or some field of the sky, those huge constellations of satellites are big problems. It's really serious. Or astronomy, because we observe, you take a photo time, maybe 1 hour or so, during this 1 hour, your
Field of view. Yeah.
Yeah. Sometimes the not just 1 or 2. So those bright satellites, because they can be small, but they are quite bright because it's quite close to the Earth. Or the trace of those satellites.
Yes. Good. Excellent. So I'm going to translate that. So give me a minute.
Yes.
Λοιπόν, ο κύριος Keiichi λέει λοιπόν το εξής. Καταρχάς, για τις δικές σου παρατηρήσεις, η σύντομη απάντηση είναι όχι, δεν επηρεάζουν τις παρατηρήσεις τους, και ο βασικός λόγος είναι ότι παρατηρούν σε ένα πολύ μικρό οπτικό πεδίο. Επειδή στην πραγματικότητα οι παρατηρήσεις είναι τόσο εστιασμένες, τόσο μεγάλης διακριτικής ικανότητας, ώστε κάποιος θα μπορούσε να δει ένα μικρό μπαλάκι του πινκ-πονγκ στην κορυφή του πύργου Άιφελ από τη Θεσσαλονίκη. Γι' αυτό το λόγο οι δικές τους παρατηρήσεις δεν θα μπορούσαν να επηρεαστούν, επειδή είναι πρακτικά σχεδόν μηδενική πιθανότητα ένας δορυφόρος να περάσει μέσα από το οπτικό πεδίο. Για παρατηρήσεις όμως μεγαλύτερης διάστασης, μεγαλύτερου οπτικού πεδίου, όπως λέμε στην παρατηρησιακή αστροφυσική, οι δορυφόροι μπορούν να κάνουν πολύ μεγάλη ζημιά. Ειδικά στις περιπτώσεις που οι παρατηρήσεις εκτείνονται στον χρόνο για αρκετές ώρες, μην ξεχνάτε ότι τα αμυδρά αντικείμενα για να τα παρατηρήσουμε, τα παρατηρούμε πάρα πολύ ώρα και συλλέγουμε φωτόνια ξανά και ξανά και ξανά μέχρι να καταφέρουμε να συλλέξουμε αρκετά μεγάλη ποσότητα φωτός που να μας δώσει μια ικανοποιητική ποιότητα στην εικόνα του αντικειμένου που παρατηρούμε. Σε αυτή την περίπτωση, επειδή και το πεδίο το οπτικό είναι μεγάλο και ο χρόνος έκθεσης είναι μεγάλος, η πιθανότητα να περάσει ένας δορυφόρος από το οπτικό πεδίο είναι πολύ μεγάλη και συνεπώς η απάντηση είναι ναι, σε αυτή την περίπτωση, κύριε Νικήτα, μπορούν να προκαλέσουν πολύ σοβαρό πρόβλημα στις παρατηρήσεις. Και the second question. Σπύρο, δώσε μας τη δεύτερη ερώτηση.
Ναι. Υπάρχει μια ερώτηση από τον κύριο Αντώνιο Κυρ. Για ποιο λόγο ένας αστέρας που φτάνει στο τέλος της ζωής του διωγγώνεται? Εδώ θα πω το εξής. Πριν από την εκπομπή, την προηγούμενη Παρασκευή, πριν από την εκπομπή που κάναμε με τον Κέιιτσι, κάναμε επίτηδες μία εκπομπή στα φυσικά με τον δόκτωρα Αντώνιο Αντωνίου, με τίτλο «Γένεση, δομή και εξέλιξη των άστρων», όπου εξηγήσαμε πάρα πολύ έτσι, με λεπτομέρειες, ο κύριος Αντωνίου εξήγησε αυτόν τον μηχανισμό, γιατί συμβαίνει αυτό. Ας μην φάμε λοιπόν πλέον χρόνο. Κύριε αγαπητέ κυβερνοθεατά, Αντώνιε Κυρ, θα σας παρακαλέσω, βρείτε λίγο χρόνο να παρακολουθήσετε εκείνη την εκπομπή, θα σας απαντήσει πάρα πολύ καλά.
Αν με επιτρέψεις να προσπαθήσω εγώ μια πολύ βιαστική και πρόχειρη απάντηση.
Ωραία, έγινε Μανώλη μου. Ναι.
Στην πραγματικότητα, κύριε Αντώνιο Κυρ, τα αστέρια όταν βρίσκονται στην κανονική κατάσταση της ζωής τους, και είναι το θερμοπυρηνικό υλικό που είναι το υδρογόνο στο πολύ κέντρο. Όταν έχουν πια κάψει τα καύσιμά τους, αρχίζει αυτό που λέμε να καταραίει ο πυρήνας. Τότε αρχίζουν να αναφλέγονται υπό συνθήκες τα εξωτερικά στρώματα. Και επειδή η καύση αντί να γίνεται στον πυρήνα, γίνεται σε στρώματα, η θερμοκρασία αυξάνει και αρχίζουν να διωγγώνονται σπρώχνοντας τα ακόμα εξωτερικότερα στρώματα προς τα πάνω. Αυτή είναι μια πρόχειρη απάντηση, αλλά καλύτερα να παρακολουθήσετε την εκπομπή την προηγούμενη.
Έχουμε μία ερώτηση ακόμη από τον κύριο Αθανασίου. Αν κάτι ανάλογο με τον αστέρα που είναι στο υποσυζήτηση θα συμβεί και με τον Μπετελκέζ ή αν συμβαίνει με τον Μπετελκέζ.
Ωραία. That's a good question. So, Mr. Athanasiou is asking whether the fate of WOH 64 is going to be the same as Betelgeuse, for example, is already happening. So, will it end up its life in the same way, or what similarities or differences? No, yes, but the evolution, the final stages of its life. Will Betelgeuse following last phases of its life, like WOH G64?
Sorry, can you repeat, because the sound quality is so poor.
So I'm asking whether Betelgeuse will finish its life in a similar way as WOH G64.
Yes. It will both of them will explode.
Okay.
The detailed of the supernova will be
good. Είναι πιθανόν, καταρχήν και οι δύο αστέρες θα τελειώσουν τη ζωή τους με ένα supernova, υπερκαινοφανή, όπως λέμε στην αστροφυσική. Οι ειδικές παράμετροι και τα ειδικά χαρακτηριστικά θα είναι διαφορετικά, διότι η εξέλιξη των αστέρων, το ξέρουμε, εξαρτάται από τις εκάστοτε συνθήκες και παραμέτρους που χαρακτηρίζουν το κάθε αστέρι. Οπότε, ποιοτικά θα είναι παρόμοιο το τέλος, με μια μεγάλη έκρηξη ενός υπερκαινοφάνους. Σπύρο, another question?
Έχουμε μία ερώτηση, θα τη μεταφράσω για τους θεατές μας που δεν ξέρουν αγγλικά, από τον φίλο τον Στέργο τον Μανόλακα, από την Ρόδο, που διατηρεί μια εξαιρετική μονάδα αστροτουρισμού στην Ρόδο. Η εστιακή απόσταση των 4 μεγάλων τηλεσκοπίων των 8 μέτρων πιστεύω δεν είναι η ίδια με αυτή των μικρών τηλεσκοπίων, των άλλων 4, τα οποία μετακινούνται κιόλας. Και τελικώς, εδώ νομίζω μάλλον κατά τη διάρκεια της παρατήρησης χρησιμοποιούν προσαρμοστικά οπτικά και τα 4 τηλεσκόπια.
Okay, good. So, Keiichi, the question is as follows. The focal length of the 4 large 8-meter telescopes, the big ones, are not of the same focal length as the small ones. When the integration, I assume, is meant, when the integration is done, do all observatories use adaptive optics?
And may I add something, Manolis?
Good. So, όχι απαραίτητα. Δεν είναι απαραίτητο ότι χρησιμοποιούν όλα adaptive. Εξαρτάται από το κάθε τηλεσκόπιο και εξαρτάται και από τις παραμέτρους της παρατήρησης κάθε φορά. Σπύρο, συγγνώμη, για πες μου, σε διέκοψα.
Θα ήθελα να ρωτήσω εάν χρησιμοποιήθηκαν και τα μεγάλα τηλεσκόπια, γιατί μου δόθηκε η εντύπωση ότι δούλεψαν σαν συμβολόμετρο τα 4 μικρά.
Πολύ σωστά. Just a clarification, Keiichi. Have you also used, that's actually unclear also to me, I must be honest. Did you also use for your observations the 8-meter telescopes? I think not. Correct? Not this time. Yeah.
We observed the same. G64 with 8-meter telescopes.
Yes, but that was for the 2007 integration, right? Yeah.
And we published the paper in 2008 and we
Yes, yes. So, Σπύρο, όχι. Σε αυτές τις παρατηρήσεις πράγματι η εντύπωση ήταν σωστή που είχαμε. Δεν χρησιμοποιήθηκαν τα 8 μέτρα.
Μόνο τα 1,8 μέτρα.
Τα 8 μέτρα όμως τηλεσκόπια χρησιμοποιήθηκαν στις παρατηρήσεις του 2005 και του 2007, που τότε, εγώ μάλιστα το θυμάμαι, λες είναι τώρα, διότι αυτή τη δουλειά την έκανε ένας διδακτορικός φοιτητής του, τον οποίο τον ήξερα πολύ καλά, γιατί διαχειριζόμουν τις σπουδές του ως coordinator στο σχολείο. Το 2005 και 2007 κάναν τις παρατηρήσεις με 2 εκ των 8 μέτρων τηλεσκόπια. Το δημοσιεύσανε το 2008, το paper τους ήταν τότε πάλι ένα press release που έκανε το ISO πάλι για το ίδιο αντίχημα. Αυτές οι μετρήσεις τους δώσανε την εκτίμηση του μεγέθους και ήταν τα δεδομένα που δώσανε για το μοντέλο, το υπολογιστικό, που προέβλεψε την ύπαρξη ενός donut, ενός τόρους, όπως μας περιέγραψε.
Ωραία. Λοιπόν, να δώσω μία ακόμη ερώτηση.
Good. Okay, so the question deals with the distance and the speed of light light and getting the information. So it says, if within a decade the star is evolving so fast, and we are 160,000 light years away, could it be that the star has already exploded long ago? That's it. Next.
This is not much speak the universe, but
Yeah.
Because it was the rest of the stage with when the star ejects so much, it's short, or it actually shorter.
Yeah.
So it's possible or maybe probable that what we are observing, the star is already gone.
Ναι, yeah.
So we don't see it. We don't
Yeah.
see it.
Η απάντηση προφανώς ναι, κύριε Κοντογιάννη. Το φως είσαι περίπου πριν από 160.000 χρόνια. Το αστέρας για εμάς. Τελευταία στάδια των αστεριών πριν εκραγούν, για χρόνια να είναι των 100 ή των 200.000 ετών. Άρα, σαφέστατα, σε τιμές κοσμικού χρόνου, το πούμε έτσι, ή απόλυτου χρόνου, ναι, θα μπορούσε να έχει εκραγεί. Εδώ όμως οφείλω και εγώ να κάνω το σχόλιο, μάλλον να μεγαλώσω λίγο το σχόλιο που έκανε ο Κέιιτσι. Να πω ότι στην αστρονομία όμως δεν μας απασχολεί στην πραγματικότητα αυτό ποτέ. Διότι οποτεδήποτε αναφερόμαστε σε χρόνους και όλη η κατανόηση της φύσης γίνεται με σχετικό τρόπο. Δηλαδή, αναφερόμαστε στα 1000 χρόνια που συζητάγαμε κατά την κουβέντα μας νωρίτερα. Εάν για παράδειγμα χρειαστούν 1000 χρόνια μέχρι να γίνει, αυτά είναι χρόνια αναφορά σε κάποια ηλικία του ιδίου του αστεριού και όχι στο δικό μας παρατηρησιακό πλαίσιο. Άρα λοιπόν, εννοώ όταν λέω ότι είναι σχετικές οι αναφορές. Είναι 1000 το αστέρι σε μια συγκεκριμένη κατάσταση, όχι από τη στιγμή που θα βρεθούμε σε μια κατάσταση. Οπότε μετράμε χρόνους του αστεριού σε σχέση με το ίδιο το αστέρι. Ας το πω με αυτόν τον τρόπο.
Πολύ ωραία. Λοιπόν, στο σημείο αυτό, Μανώλη, θα σε παρακαλέσω να ευχαριστήσεις τον Κέιιτσι και να του πεις ότι θα δώσουμε νέο ραντεβού με νέες ανακαλύψεις του.
Yes. So, Keiichi, I think that I'm speaking on behalf of everyone that is thanking you very, very much. I think people have been very excited to follow your all the wonderful things that you had to say. And Spiros renewing the appointment with you, and in the future at another call. So everybody is thanking you very, very much. Yes, I will repeat again. So I'm saying that I speak on behalf of everyone. That we thank you very much. I think people have been excited to follow the wonderful and exciting things that you have to share with that. And Spiros insists on renewing the appointment with you in the near future, and even more exciting of your research findings in the future. Thank you, Keiichi. Okay.
Okay. Just tell you all, thank you for your attention.
Yes, thank you, Keiichi. Αυτό σας ευχαριστώ πάρα πολύ όλους. Wow. Περισσότερο από το 89% του πληθυσμού στη Χιλή είναι χωρίς ηλεκτρισμό αυτή τη στιγμή. Σας ζητάει συγγνώμη για όλες τις τεχνικές δυσκολίες και σας ευχαριστώ πάρα πολύ για την προσοχή σας.
89% του πληθυσμού. Τόσο μεγάλη. Blackout γενικό δηλαδή.
89, right? 89. 98. 98. Oh, my. Wow. Okay. Interesting. So it's going to be in the news tomorrow everywhere.
Nice.
Have a very good day. Enjoy the rest of the day. It's time. Take care. Stay in touch. Bye-bye. Bye-bye.
Ίσως είναι η υπερφόρτωση των δικτύων λόγω του ότι είναι καλοκαίρι εκεί. Είναι ώρα απογευματινή. Προφανώς τα κλιματιστικά πήραν μπροστά και πάθαν blackout. Εντάξει, λοιπόν, θέλουμε να ευχαριστήσουμε και τους πολυάριθμους κυβερνοθεατές μας και μάλιστα όλους αυτούς που μέσα από τα chat του YouTube και του Facebook μας συντρόφευσαν αυτές τις κοντά 2 ώρες πήγε τελικά η εκπομπή μας. Θα δώσουμε ραντεβού την μεθεπόμενη Παρασκευή, 7 Μαρτίου 2025, με μια εξαιρετικά ενδιαφέρουσα εκπομπή με τίτλο «Η γεωλογία στο ηλιακό μας σύστημα». Προσκεκλημένη μου θα είναι η Βασίλης Μέλφος, καθηγητής κοιτασματολογίας γεωχημίας στο τμήμα γεωλογίας του Απιθύτα, ο Ιωάννης Μπαζιώτης, αναπληρωτής καθηγητής ορεικτολογίας πετρολογίας του Γεωπονικού Πανεπιστημίου Αθηνών και η Ανεζίνα Σολομονίδου, πλανητικός γεωλόγος, τέλεχος του Ελληνικού Κέντρου Διαστήματος. Μανώλη, στο σημείο αυτό θέλω να σε ευχαριστήσω από καρδιάς για όλο αυτό τον τεράστιο κόπο τον οποίο κατέβαλες και την εξαιρετική δουλειά που έκανες. Λοιπόν, και να τα πούμε σύντομα και εμείς.
Εγώ ευχαριστώ για την πρόσκληση.
Λοιπόν, αγαπητοί φίλοι και αγαπητές φίλες, σας ευχόμαστε να είστε όλοι και όλες καλά. Καληνύχτα σας.